Okay, welcome back. This is the third part of our lesson today on Apologiochemistry, Module 11. If you're following along with me, we are at this point on page 367. And we're going to be talking about a new concept now. Up until this point, we have talked about the word molarity being one way to represent the concentration of a solution. And we said molarity was designated with a capital M, and it's the moles of solute per liter of solution. We're going to switch gears now. We're going to talk about a new concept that has to do with the concentration of a solution. This new concept is molality. Molality. Notice that's designated with a small letter m. And it's a different concept entirely because it's the moles of solute divided by the kilograms of solvent. The moles of solute divided by the kilograms of solvent. Notice with molarity, it's moles of solute per liter of solution. Here it's solute with solvent, not solution. Okay, so we're going to look at some examples of that. If you look in your book on page 368, you're going to see example 11.2 walks you through several of those. Some of them are just straight up calculations, and some of them require you to go from grams to moles to make that calculation to find the number of moles of solute. I'm going to do specifically for you, we're going to talk about the on your own 11.6, and the problem says calculate the molarity, little m, molality, little m, molality. So we're going to calculate the molality, little m. We're not going to be using molarity in this section. We're going to be using molality, the new concept. So again, that's going to be the moles of solute divided by the kilogram of solvent, and it will tell you that. So for number A, it says you have 2.3 moles of NaOH. That is your solute, in 1.2 kilograms of water. That is your solvent. So you have 2.3 moles of NaH and 1.2 kilograms of H2O. The solute divided by the solvent. So that's just a straight up calculation. You're going to have the moles of solute divided by the kilograms of solvent just by definition for molality. And that's going to be 2.5. Whoops, I wrote 2.5 and it's actually 2.3. Sorry about that. 2.3 moles of NaOH divided by 1.2 kilograms of water. That's going to give you a molality of 1.9, a concentration in molality, little m, which is moles per kilogram of solvent, of 1.9. Now, problem B is a little bit different, only because they give you the solute in grams as opposed to in moles. And we know by definition we're going to have to get it to moles. So what do? We just convert grams to moles, just like we've always done with the stoichiometry problems. In this case, we know we have 250 grams of KNO3 in 2.43 kilograms of water. And we notice right away that this is the right units because it's going to be moles per kilogram. So we're okay with that. We're not going to have to convert. But we are going to have to convert from grams of KNO3 to moles of KNO3. And we go back and we use our gram formula weight. We add up the K, the N, and 3 of the oxygens to find that there are 101.1 grams of KNO3 for every mole of KNO3. So the number of moles is going to be 2.47 moles, and then the molality is going to be the number of moles divided by the kilograms given here. So it's going to be 2.47 moles divided by 2.43 kilograms, making it 1.2 little m molality. Okay, now I want you to try the on your own number C on your own. And again, you're going to have two calculations here. You're going to have to go to grams to go from the grams given to the moles of NaBr, and it gives you the in grams, and you're going to have to go to kilograms of water. Okay, so you have to make two different calculations there. You're going to have to go from grams to moles and from grams to kilograms. Try that on your own right now. On your own, number C, page 369. Okay, and see if you can get that. If you need to look at the end of the chapter, it also shows you how to do that solution. But we're going to move on and talk about the next concept. Believe it or not, we're almost done with the chapter. The next concept we're going to talk about is a formula for freezing point depression, which is really applicable this time of year because you'll notice that the roads are freezing, which is why we're not in class today. because the roads are frozen. And you probably noticed that there were people out putting solutions of salt on the road to help lower the freezing point, to make it so that the ice turns to water. When you add a solute, the freezing point's going to be lowered. So if you add salt to the ice on the roads, it lowers the freezing point and makes it so that it's not as icy. And the formula for that is 11.2. It's at the bottom of page 370. And it says the change in temperature is the number of ions present times the freezing point constant times molality. Remember that concept, molality, moles of solute per kilogram of solvent. This is where this plays out. So what happens is, if you have more ions in a solution, it will lower that freezing point even more. That Kf, that freezing point constant, will always be given to you, okay? Or you'll be able to look it up off a chart. You'll never see that unless you're solving for that. But that's a given, that's a constant. And then molality, that's the thing that you may be asked to calculate. So let's look at an example of that. Let's look at page 373 on your own, 11.8. Now, before you look at that, I'd like you to take a look at example 11.3. That's on page 371. Go ahead and read through that and make sure that you understand that. There are several examples of calculating that freezing point. And then I want you to look at example 11.8 on your own. And here's what it says. It says if a solution is made by dissolving 2.3 grams of MgOH2 into 25 grams of acetic acid, what is the freezing point? And it tells you that freezing point constant for acetic acid is 3.90 degrees C per molality, and the freezing point of pure acetic acid is 16.6 degrees C. So let's take a look at this and see how we figure this out. And always we ask, what equation are we going to need? Well, we're going to need that freezing point equation, which says delta T is the number of ions times the freezing point constant times the molality. The second step is going to be, what do you know? Where do you want to go, right? It always is. So what do we know? What do we know? Well, we know that we have 2.3 grams of MgOH2, but we know we're going to have to convert that to moles. By definition, it's moles per kilogram. And we know that we have a number of grams of the acetic acid, which is your solvent. Okay, so you have 2.3 grams and 25 grams. And one we're going to have to convert to moles, and one we're going to have to convert to kilograms. So the first step is to find the number of moles of the solute. So we said we had 2.3 grams of MgOH2. And we figured the gram formula weight for that was 58.3 grams for every mole. So we can just do that calculation where we convert from grams to moles to find that we have 0.0395 moles of MgOH2 when we do the calculation out. Okay, so then there was 58.3 grams per mole. We took 2.3 divided by 58.3, and we found there was 0.395 moles. Now, the next thing we have to do is convert the number of grams given of acetic acid to kilograms, because that's the definition of molality. Moles of solute per kilograms of solvent, and we're given it in grams. Therefore, we know we have to convert to kilograms, and you just divide by 1,000. You go boom, boom, boom. And so 0.25 grams is going to be 0.025 kilograms. It's going to convert to kilograms. And so now we can use that definition of molality, which is the number of moles of the solute divided by the kilograms of the solvent. We get our moles of solute over here. We calculated our kilograms of solvent here, and we divide that. And that tells us that we have 0.58 molality, little m. Okay, it's a concentration unit, and that's what we have. And that's what we need to solve this. Delta T equals negative I times the freezing point constant times the molality. We just solved for the molality. Once we plug all that in, you're asking, okay, well, I know what the molality is, and it told me the freezing point constant, so I know that. But the one thing I don't know is the number of ions. How many ions? How am I going to figure that out? Okay, well, let's look at what you have here. You have magnesium, and you have hydroxide, and if you separated that out, you know that it would be magnesium with a +1 charge and hydroxide with a +2 and hydroxide with a -1. So that's a total of 3 ions. 2 and 1 is 3. So that means that your I is going to be 3. So when we plug all that in, it's negative 3, which is the number of ions. 1 plus 2 is 3. Multiply that by our molality, which we solved right here, 0.058 molality. Multiply that by our freezing point constant, which is 3.9 degrees C per molality. And that's going to give us an answer of the delta T being negative 18.5 degrees centigrade. But that's not your final answer. The question says, what is the freezing point? And it gives you the freezing point of pure acetic acid to be 16.6 degrees C, but this is not pure. Remember, it has that solute added to it. So we have to take that change, that delta T, delta meaning change, negative 18.5, add the freezing point of what it would be if it did not have anything in it, and we're going to find that the actual freezing point is going to be negative 1.9 degrees C. And you can see that solved out at the end of the chapter. He walks through all of the on your owns. We have one more concept to talk about. We're going to be talking about a very similar concept called boiling point elevation, and then, guys, we're done with this chapter. So I really want you to watch these videos so that I don't need to spend the time on this on Monday. I'm going to breeze through this really fast on Monday, and then we're going to be moving into Module 12. So we'll take a break, and I'll be talking about boiling point elevation in just a couple minutes. Thanks.